In this image, you can see the Earth and the Moon drawn to the correct scale, so hopefully you can see the Earth there and the Moon here. Let's label them E and M, Earth and Moon. Okay, so they mutually attract one another, which causes them to orbit around their common center of mass. And that attraction is, as you know, governed by the law of gravity. So there's this force that can be represented by this equation. So take the mass of the Earth, we'll call Earth object number 1. Take the mass of the Moon, call that object number 2. And then divide by the distance between the two of them, which is roughly 60 times the radius of the Earth. So that distance we can label here as little r, if we want, indicate that it's 60 times RE, 60 times the radius of the Earth. Okay, so that r is squared in this equation, and then there's a constant of proportionality. This is the exact same law that you would use to find the force of attraction between you and the Earth. The only difference is you're not at a distance of 60 times the radius of the Earth away from the Earth. You're 1 Earth radius away from the Earth. Now, this figure is clearly not drawn to scale, but the distance between you and the center of the Earth is, of course, just 1 Earth radius. So, same equation in both cases, and in fact, if we apply this equation to the case of you and the Earth, then we'll say you're object number 1, the Earth is object number 2. So I'm not sure what your mass is, but I know the mass of the Earth. It's about 6.0 times 10 to the 24th kilograms. And I know the radius of the Earth. It's about 6.4 times 10 to the 6 meters. And I know the value of this universal constant g. It's about 6.67 times 10 to the negative 11th. The units are a little complicated, but they're newtons times square meters divided by kilograms squared. So if you put this all together, you can plug in all of the numbers except for this mass number 1. And so you'd find the force between you and the Earth can be found by multiplying your mass times all this other stuff, which would be g times the mass of the Earth divided by the radius of the Earth squared. Well, if you grab a calculator and use these given numbers, you can figure out what that calculates out to. And it's no surprise, it comes out to be 9.8, and the units you're left with, well, let's see. I guess it would be newtons per kilogram. Because after all, these meters, according to this formula, are going to get squared. So they'll cancel with those meters squared. That kilogram will cancel one of these kilograms. Yeah, you'd be left with newtons per kilogram. Now, recall that a newton is the same thing as a kilogram meter per second squared. So then what the heck is a newton per kilogram? A newton per kilogram would be the same thing as a meter per second squared. So if we wanted, we could say this is the same as 9.8 meters per second squared. Now you definitely recognize this. This is lowercase g, the acceleration due to gravity at the surface of the Earth. So for now, we're not going to use the formula in this form when trying to calculate forces of gravity, because we're always going to find the force of gravity for things that are located very near the surface of the Earth. So we can just use a shortcut and say the force is equal to the mass of the object at the surface of the Earth multiplied by the Earth's acceleration due to gravity. So there's no distinction between these two formulas, but it's much easier to use in this form. Now, by the way, it should be clear that the value of 9.8 meters per second squared, which can also be expressed as 9.8 newtons per kilogram, is very specific to the surface of the Earth. Because the force of gravity is actually an inverse squared law, you could ask the question, if I'm attracted to the Earth by a gravitational field strength of 9.8 newtons per kilogram when standing on the surface of the Earth, what would be the force of attraction if you were located not 1 Earth radius away from the center of the Earth, but 2 Earth radii. In other words, you double your distance. Well, certainly the attraction should go down if you're farther away. This is how all these action at a distance forces work. Gravity is definitely an example of action at a distance, right? The Earth and the Moon have this great separation between them, yet they can still both feel this mutual force of attraction toward one another. So this is what we mean by action at a distance. Again, you might not think of you standing on the Earth as action at a distance because you might think you're touching the Earth, but really you're at a distance of 1 Earth radius away from the center, right? We need to measure from the center of your body to the center of the Earth. So gravity is an action at a distance kind of force, and the greater the distance between the two objects, the weaker or the smaller the force. But it's not a strict inverse proportionality. Doubling the distance doesn't cut the force in half. Actually, when you take the distance and multiply it by 2, it leads to 1/4 of the force. If you take the distance and multiply it by 3, it would lead to 1/9 of the force. If you took the distance and multiplied by 4, you guessed it, you get 1/16 of the force. This is the idea of an inverse squared law. And you can see it in the original form of the equation, where the r is in the denominator of the equation, thus inverse proportionality, and of course the r is squared, so that's the nature of this term, inverse squared law. There's the Earth. There's a location where g is equal to 9.8. If you go one more Earth radius up above the Earth, that's not a location where the acceleration due to gravity is 4.9. At this point, it would be about roughly 2.5 meters per second squared. One more Earth radius, so now we're at not r, not 2r, but 3r, and so the force goes down not just to 1/4, but to 1/9, and 1/9 of 9.8 would be approximately 1.1 meters per second squared, and on and on and on you can go and see how rapidly the gravitational field strength drops off. Okay, this same sort of behavior governs electrostatic interactions. If you take a couple balloons and hang them from some strings from the ceiling, you could get a rabbit's fur or a piece of wool and rub the balloons, and you end up putting an electrostatic charge on them. So maybe you strip electrons off of both of the balloons. Then in that case, if both balloons are lacking in electrons, they'd each have a net positive charge. So here we don't use the symbol M for mass, we use the symbol Q for charge. So if the balloon on the left is object number 1 and the balloon on the right is object number 2, we can say there's an electric charge on the balloon on the left called Q1 and an electric charge on the balloon on the right, Q2. Now, we've already seen Newton's law of gravity expressed as a universal constant times the mass of the Earth times the mass of the Moon, for example, divided by the distance between them squared. In the case of electrostatics, we say the force is equal to a universal constant, a different value in this case, multiplied by the charge on one object times the charge on the other object, but again divided by the distance between the two of them squared. So if we measure the distance from the center of one balloon to the center of the other, there's this quantity r. So it's interesting to see that another one of the 4 fundamental forces, gravity versus electrostatics, are both governed by an inverse squared law. It turns out that all contact forces are electrostatic in nature. So I would argue that when you take your hand and try to knock on wood, you never really make contact if your definition of contact is that matter has no space between it. In other words, there's an electron cloud around all the atoms that make up any object, whether that be your knuckles or the desk. And so there's a repulsion between the electron clouds for the atoms at the tips of your knuckles and the electron clouds on the surface of the desk. And then there's space between those, but they get close enough. And this equation for electrostatic force says as this distance r gets smaller, the force rapidly gets much, much greater because it's an inverse squared kind of law. And so contact is really just getting to the point where the electrostatic force is large enough that you can feel it. So in that regard, I don't think our feet really ever completely touch the ground if your definition of touch is no space between the matter. It's just that the electrons in the very bottom of the soles of your shoes and the electrons on the surface of the ground get close enough that they repel to the point that that force is appreciable. This same sort of law governs the behavior of magnetism as well. We'll see an inverse squared law in that case. If you take two wires and an electric current flows in one, the current flowing in wire number one has the ability to influence and exert a force as long as there's some amount of current flowing in wire number two. So in this case, an electric current is really a form of charge in motion, and the electric charges that are drifting through the two wires have a way of influencing each other with an action at a distance sort of behavior. So we can say r is the distance between the two wires. And we'll find in the next semester in physics that there's an inverse squared law that also governs magnetic forces. So there's an introduction to inverse squared laws and the way in which contact forces, in a way, have a relationship that's similar to gravitational forces. So thanks for watching, and stay tuned for the next step.